In this chapter, we'll introduce a quick start guide for using the Bus Expert 2, B2. This guide is specifically designed for those who are new to B2 or want to use the device more efficiently. Whether you're a beginner or an advanced user, you'll quickly get the hang of the basic operations of the B2. We'll also explain the two main operating modes that the B2 supports, the Logic Analyzer mode and the Protocol Analyzer mode. These modes can be selected based on your testing needs. The B2 allows for quick switching between these operating modes, which is crucial for handling different types of testing scenarios. Depending on your requirements, you can easily switch between Logic Analyzer mode and Protocol Analyzer mode without having to restart the device or perform any complex configurations. Connect the B2 to your computer and launch the Bus Expert software. Once the software is running, you'll need to follow these steps. Choose the operating mode, either LA or PA, and set the frequency and channels. Adjust the basic parameters like trigger conditions and sampling rate. I'll now explain each step in more detail. In Logic Analyzer mode, our main task is to perform signal timing analysis. Now, we'll walk through how to set the sampling rate and the impact of the sampling rate on signal capture. The sampling rate refers to how many times the device collects data per second, and it's one of the key parameters for analyzing signals. When performing signal timing analysis, you need to set an appropriate sampling rate to capture the necessary signal details. The B2 offers a sampling rate range from 5 MHz to 2 GHz. This means you can choose the right sampling rate range based on your testing needs. Generally, to ensure accurate signal capture, the sampling rate should be set to 6 to 10 times the signal's highest frequency. This ensures there are enough samples in each signal cycle to accurately reconstruct the waveform and avoid missing key details. For example, if the signal you're testing has a frequency of 100 MHz, setting the sampling rate between 800 MHz and 1 GHz will be enough to capture the main features of the signal. When testing signals with very high frequencies, especially with digital communication interfaces like eMMC HS400, we recommend using a 2 GHz sampling rate. High-frequency signals change very quickly, and a higher sampling rate is needed to capture more waveform details, preventing distortion or loss of critical information. In Logic Analyzer mode, besides setting the sampling rate, there's another important parameter that needs to be configured: memory depth. Memory depth determines how much data we can record and capture, and it affects the measurement duration and the device's ability to store data. Now, let's dive into how to choose the right memory depth. Memory depth refers to how much data the analyzer can store, typically measured in samples. This is directly related to the duration of the signal you're measuring and the sampling frequency. The memory depth of the B2 ranges from 2K to 2 billion samples. This means you can choose an appropriate memory depth based on your testing needs. The sampling frequency is how many times per second the device collects data. The higher the sampling frequency, the more samples it collects each second. For example, if the sampling rate is set to 1 GHz, it will collect 1 billion samples per second. Memory depth refers to how many samples the logic analyzer can store internally. Generally, the larger the memory depth, the longer the measurement duration you can record. The size of the memory directly impacts how long you can record and observe a test. For example, if your device has 100 million samples of memory and you set the sampling frequency to 1 GHz, you'll be able to record 100 milliseconds of signal waveform. On the flip side, if you need to measure a longer signal duration, you can reduce the sampling frequency to extend the recording time. For instance, if you set the sampling frequency to 100 MHz, you'll be able to record 1 second of signal with the same memory size. If you choose a higher sampling frequency, like 1 GHz or 2 GHz, the memory depth must be relatively large to ensure you can record a sufficiently long signal during the measurement. If the signal frequency is low, you can select a smaller memory depth for the measurement, as less data is collected per second, allowing for longer recording times. Example, let's say you set the sampling rate of the B2 to 2 GHz, and the device has a memory capacity of 2 billion samples. In this case, the memory depth allows you to record 1 second of signal data. Now, if you lower the sampling rate to 500 MHz with the same memory depth, you would be able to capture 4 seconds of signal data. If you need to record a signal for a long period or monitor for an extended time, it's crucial to choose a larger memory depth. This ensures the measurement won't be interrupted when the memory gets full. If your measurement requires precise capture of every detail of the signal, selecting the right memory depth ensures that even at high sampling frequencies, you'll still be able to record a long enough duration for accurate analysis. By choosing the appropriate memory depth, you'll be able to better capture and analyze signals, improving both the efficiency and accuracy of your measurements. In Logic Analyzer mode, the trigger conditions are the foundation for setting up signal capture. They determine the point at which the measurement process begins. The way you set the trigger point directly affects the range of the signal you can capture. Now, let's take a closer look at how to set up trigger conditions to improve your testing efficiency. Setting trigger conditions is a key step in the Logic Analyzer's signal timing analysis. The trigger condition decides when to start recording the signal and when to stop recording it. The trigger position determines how long the instrument continues to record the signal after the trigger condition is met. For example, if you set the trigger position to 10%, when the trigger condition is satisfied, the instrument will continue recording 90% of the memory depth's data. You can set the trigger to start the recording, with the trigger position set to 10%. This way, 90% of the memory will be available to check if the result is correct. Alternatively, you could set the trigger to detect when an error occurs, with the trigger position set to 90%. This will leave 90% of the memory to examine the cause of the issue. The trigger point setup will depend on the specific test requirements. For example, when we need to detect a particular event, such as a change in transmission mode with CMD6 or data transfer with CMD17/CMD18/CMD24/CMD25, we can set the trigger point at these specific signal events. In the B2 software interface, you can set various trigger conditions, including but not limited to the following common setups. Edge trigger, trigger recording when there is a change in signal level, either rising edge or falling edge. Pulse width trigger, trigger recording when the signal duration reaches a set threshold. Logical condition trigger, set a trigger based on logical combinations of multiple signals. For example, trigger recording when certain signals meet specific conditions simultaneously. Event trigger, trigger recording when the bus matches a specific packet or encounters a particular error. Accurate trigger condition settings are critical for the test's precision. Depending on the test requirements, you can choose the most suitable trigger condition, which will help avoid interference from unrelated signals and only capture the signal range you're concerned with. For instance, when analyzing data communication, you could set the trigger point to the start of data or a specific command byte. This ensures that the test begins at the correct moment, improving both the efficiency and accuracy of the test. By setting precise trigger conditions, you'll be able to capture and analyze signals more effectively, leading to more accurate and reliable test results. Next, let's go over how to effectively start the test and perform signal capture. Before you start the test, the first thing you'll need to do is press the Signal Capture button to begin data capture. This will trigger the B2 to start monitoring and recording the signals from all channels. Important, before doing this, make sure that all hardware connections are correct and secure. This includes checking that the probes are properly connected and ensuring that all conditions in your test environment, such as voltage and signal strength, are properly set. After performing the signal capture, the next step is to power on the device under test. This ensures that signal capture begins as soon as the DUT starts operating. Why do we do this? Once you initiate signal capture and turn on the DUT, the Logic Analyzer will start capturing the signals emitted by the DUT. During this process, the recorded signals will reflect the actual operation of the DUT, which helps in analyzing its behavior and the accuracy of the signal transmission. Once the test is complete, you can begin reviewing the timing waveforms and bus waveforms captured by the instrument. This is a crucial step for performing further analysis and diagnostics. Before setting up the decoding parameters, we first need to choose which bus protocol we want to analyze, whether it's eMMC, SD, SDIO, or toggle DDR. You can select the protocol type from the sample drop-down menu and then choose Add Bus Protocol from the window that pops up to select the bus protocol you want to work with. Setting the correct decoding parameters helps you extract protocol-level information from the raw signals, allowing you to better understand the signal's meaning and how to troubleshoot issues. Here's a detailed explanation of how to set the decoding parameters. First, you need to configure the decoding parameters based on the protocol version, transmission format, and data length used by the device under test. A common data length is 512 bytes. Next, set up the decoding options by selecting the items you want to decode, such as CMD decoding or data decoding. Then, configure the channels. Typically, clock is assigned to A0, command to A1, and data to A2, and so on. By correctly setting the decoding parameters, you'll be able to fully leverage the B2's decoding capabilities, perform accurate signal timing analysis for various protocols, and obtain valuable test results. In Logic Analyzer mode, after completing the signal timing analysis, saving the test results not only helps with subsequent data analysis but also makes it easier to record and organize key information from the testing process. The data saving process involves storing the measurement results in various file formats, such as text files or .csv files, so you can review the results anytime or share the data with other team members for further analysis. From the File drop-down menu, you can choose Export and then select either Waveform Export or Packet List Export. You can set the range to export, whether parameters should be included, and whether to export headers. If you choose to export as a .csv file, you can save the test data in a tabular format, making it easier to process in data analysis tools like Excel. If you choose to export as a text file, you can view the data in a text editor, or you can write custom analysis software for further processing. By performing these data-saving operations, you'll be able to better manage your test results and conduct subsequent analysis and sharing, helping to improve the efficiency of your testing work. 4.0 Mini. In Protocol Analyzer mode, you'll be performing protocol-level analysis to extract and interpret specific protocol data from the electrical signals. To ensure accurate measurement results, we first need to set up proper hardware connections and select the correct protocol. Now, let's dive into how to set up these basic steps. Before performing protocol analysis, proper wiring is key to successful measurements. Here are the specific steps for wiring. Connect the clock signal to channel A0. This will help you synchronize the analysis of subsequent signals. The clock signal is the foundation for most protocol analyses because it dictates the timing for data transmission and reception. Connect the command line to channel A1. Command is the main signal for control instructions, used to manage the transmission of protocol commands. In many memory protocols, the command line is used to send read, write, and other operational commands. Connect the data lines, D0, D1, D2, D3, etc., to channels A2, A3, and so on. These data lines carry the actual data or command parameters, making them one of the most important signals in the protocol. These wiring setups ensure that each channel correctly receives the related signals from the protocol, allowing you to capture and decode the protocol data. Before you begin in PA mode, make sure to verify the wiring in LA mode first. Ensure that it's secure and stable with no voltage spikes, check that the CRC for command and data is correct, and that the trigger levels and I/O delays have been effectively calibrated. In PA mode, depending on your testing requirements, you'll need to choose the appropriate protocol for analysis. eMMC. If you're analyzing the eMMC protocol, selecting this mode allows you to monitor and decode commands, data transfers, and status reports from eMMC devices. SD. If your device under test is an SD card, select the SD protocol mode. This will focus on the SD card communication protocol, including card initialization, data transfer, and error handling. By setting up the correct wiring and selecting the proper protocol, you'll be ready to conduct thorough and accurate protocol analysis. Next, we'll talk about how to set up recording conditions to achieve the best test results. Once your device under test, like an eMMC or SD card, is up and running, you'll need to set the correct bus width and bus length based on the actual configuration. These settings help you capture every bit of data accurately and ensure that the measurement signals cover the necessary range. This refers to the number of signal lines that can transmit data simultaneously. For example, if you're working with a 4-bit wide SD bus, you'll need to set the bus width to 4. For an 8-bit wide eMMC bus, set it to 8. This parameter refers to the data packet length of the device under test. Typically, this is set to 512 bytes. You can choose to record specific packets or all packets, depending on your testing requirements. When doing long-term recordings, especially when you need to monitor extended operations or large-scale data transfers, it's crucial to ensure you have enough hard drive space to store the data. In long-term recording mode, you can specify where to store the recorded data, such as a particular hard drive or folder. Make sure the chosen storage device has enough space to accommodate large amounts of data. The hard drive's transfer speed will also affect the data bandwidth during long-term recordings. Before starting long-term recording, the software will check the available space on the hard drive to ensure you don't run out of storage and interrupt the recording process. By following these steps, you'll be able to set up optimal recording conditions for your tests and ensure that the data is captured effectively and stored without interruptions. In Protocol Analyzer mode, packet analysis is one of the key steps in protocol diagnostics and troubleshooting. Today, we'll go over how to perform packet analysis, including automatic decoding, packet data display, command classification, and packet count statistics. In PA mode, automatic decoding is one of the most basic and useful features. Once you successfully connect the test device and start recording data, Bus Expert 2 will automatically decode and sequentially display the protocol packet data based on the protocol you've selected. Command classification is a critical part of protocol analysis. In PA mode, you can use the command sort window to view all the packets and see commands grouped by events. You'll also be able to count the occurrences of each event. The packet count statistics feature shows how many times each type of command or packet appears. This is really helpful for analyzing system behavior. By checking the count statistics, you can quickly understand how often certain commands or packets appear during the test. This feature displays the count statistics for various commands or packets, helping you understand how often different types of packets appear during specific time periods. For example, you might find that some packets appear unusually frequently, which could be a sign of an issue. This could prompt you to check for system design flaws or signal transmission problems. By reviewing the statistical results of different packets, you can identify unusual changes in the packet count. This can help you spot potential errors or issues. For instance, if a particular packet appears too frequently, it may indicate that a command is being sent repeatedly during certain processes or that the hardware is making frequent retry attempts due to errors. The packet sorting feature allows you to sort the captured packets based on different criteria, such as time, command type, or data size. You can choose to sort packets by the time they were captured, which helps you clearly see the order in which packets were transmitted during communication. This is crucial for analyzing data flow changes. Additionally, you can sort by command type, making it easier to view how commands of the same type are distributed. The sorting feature allows you to focus on specific packets or commands, narrowing down the analysis scope. This makes it easier to troubleshoot and enhances testing accuracy and efficiency. These analysis functions work together to give you a comprehensive understanding of the protocol operation of the device under test, improving your testing efficiency, accuracy, and making it easier to pinpoint any issues.